Hello friends, have you ever tried to solve a quadratic equation geometrically? Like we generally use the quadratic formula to solve the quadratic equation, but today we are going to solve the quadratic equation using only geometry. So let's proceed. First, I'll take a simple example of a quadratic equation to clarify you. So this will be the quadratic equation. So in this quadratic equation, the sum of two numbers is equal to negative of this coefficient, which is equal to 7, and the product of two numbers is equal to 12, which is the constant term. So at first, let's take a rope or a length of 7 units. So this 7 units is nothing but the sum of two numbers. So we take a length of 7 units. Then by taking this as a diameter of a circle, we draw a circle like this. Now, we already know the product of two numbers is 12, so it can be interpreted as a square having area of 12. So we imagine a square having area 12. So if the area of this square is 12, then the length of each side should be square root of 12, which is approximately equal to 3.5. So we draw a square with length 3.5 units. In the next step, we move this square to the circle, and we move it in such a way that the base just lies on the diameter of the circle and the corner of the square meets the circle at the circumference somewhere here. Then we measure the distance of the base in which the square lies. So the distance from this point is 3, and the remaining distance is 4. So we got the solutions of the quadratic equation to be 3 and 4. So by using the quadratic equation also, or by using the factorization process, we also get the same result as 4 and 3. So let's talk about why this idea works. At first, what we have done is we have assumed the sum of two numbers to be s. So we already know this length of rope to be s, and this s can be represented in such a way that it consists the sum of two numbers, say x and y. And we have imagined a square whose area is b, and its side of the square will be square root of b. Now, to describe why it works, we have an interesting theorem on circle. Let's see this circle. In this circle, let's assume this as this length as t, and this length will also be t, since this diameter bisects this chord. Then we have already talked this length as x and this length as y, and in a circle the interesting relation is the product of the two lengths x and y is equal to the product of this two lengths t and t, so t squared. Hence t is nothing but square root of x of y. Hence this length is nothing but square root of x and y. And since square root of p is also equal to square root of xy, when we put this square on the base of the diameter like this, when the square's corner is just touching the circumference over here, then it divides this length or diameter into two segments in such a way that it gives the two numbers x and y. So this is all about the explanation. Now let's go to another problem. Now I have taken a new example in which I have switched the sign of this coefficient. I have taken plus 7 instead of minus 7, and let's see what happens. Now the sum of two numbers will be minus 7 as the negative of this coefficient, and the product of two numbers is the same, that is 12. So in this case also we can proceed with the same method that we used earlier. So the answers will be the same, the lengths will be 4 and 3, but the only thing that we need to remember is the sum of two numbers is minus 7, And since the product of two numbers is 12, that implies both the numbers should have the same sign, either plus plus or minus minus. Since the result are 4 and 3 and the sum is negative of 7, so they both should be in negative sign. So the result will be minus 4 and minus 3. Now I am taking a bit more complex example. Here the sum of two numbers is 1 as the negative of this coefficient, and the product of two numbers is negative of 12. For these type of situations we can use this method. First let's try the same square. First let's imagine the same square having area of 12 square units. So the length of each side will be square root of 12, which is approximately 3.5 units. Then what we do is we extend a line in the base like this, whose length is half of this number. So half of 1 is 0.5. Hence we measure a length of 0.5 units and draw it like this. Then we draw a diagonal in which this is actually a right angle triangle. Then we draw a circle considering this as the center of circle. Then we can extend the radius of the circle to make it as a diameter. Now we can use the same method that we used earlier, like this will be the square and this will be the circle. Now we put this square on the diameter of the circle in such a way that the corner of the square just touches the circumference at this point. Now we measure the distance from here to here, which is 3, and we measure the distance from here to here as 4. So the two solutions seem to be 3 and 4. But the main question is the product of two numbers is minus 12. Hence, if 4 and 3 are two numbers, then they must be opposite in sign. Hence, the solution will either be minus 3 plus 4 or minus 4 and plus 3. But since the sum of two numbers is 1, hence this is the more feasible result. So the solutions will be 4 and minus 3. Let's again change this problem where I change the sign of this coefficient. Now the sum of two numbers will be minus 1. We can proceed in the same process, and the two solutions seem to be 3 and 4. But since the product is negative, hence we can get two feasible solutions as plus 3 and minus 4, or plus 4 and minus 3. Since the sum of two numbers is minus 1, so plus 3 and minus 4 will be the feasible solution over here. So I haven't talked about why this second method works for these types of situations. So I have left this question for the audience to find out. So from this method we can solve any type of quadratic equation that either may be in the form of plus bx plus c or minus bx minus c or minus bx plus c or plus bx and minus c, so which includes every type of quadratic equations. So thanks for watching.